think about the situation which can be modeled by motion with constant acceleration. As I previously said, this is rarely an exact description, but can be a good approximation. In particular, in the absence of air resistance, objects free falling under gravity will accelerate at a constant rate. We'll also often model cars speeding up or braking as motion with constant acceleration. Whenever the velocity is changing, and we're not don't care so much about the details of how it's changing, constant acceleration can be a good way to think about it. If the acceleration is constant, then it's very easy to draw an acceleration versus time graph. It's going to look something like this, where I will call this time 0. Okay. So suppose I want to know how much the velocity changes between time 0 and some later time. And I think logic is simplest if I call this later time TF. Though sometimes we'll make this argument just calling it T. So we know the change in the velocity is just the area under this curve. So that's this area. All right. The height of this curve is A. And the width of this rectangle is TF. So in other words, V of TF is equal to V at time 0 plus ATF. And I usually introduce a new symbol for the velocity at time 0, and I call this V sub 0. Now this actually should look familiar to you. If I gave you the calculus problem of what is the integral a dt, where a was a constant, recall we're doing motion with constant acceleration, all right, you would say that this is equal to at plus a constant. And in your calculus class, you might have done something like that. This is exactly the same argument as we have here. That if I just put t set, tf is just some particular time, call that time t, I get v of t equals v naught plus at and that's the constant. Okay, let's now get back to the problem at hand, thinking about this this physics of this object moving with constant acceleration. So what we see is that the velocity increases at a constant rate. Right? That makes sense. You have a constant acceleration, you have a constant rate of increase of velocity. And I'm going to draw a graph of this, and I guess there's two possible cases I can do. I can do the case where V naught is positive and the case where V naught is negative. Let me first do V naught positive. It doesn't look that much different in the two cases. Okay. So if I put V naught here and 0 here, I just get a line of constant slope, and that slope is just the acceleration. Okay. Now, if V naught was negative, instead I would have started this curve, instead of up here at some positive value, I would have started at some negative value here, right? But it would again just look like that same curve. Now you can probably guess what we're going to do next is we're going to try and calculate the position, or rather, what is the change of position from time 0. So once again, if I introduce some time tf, the change in position is going to be this area here, right? Which is a trapezoid. And you can probably remember your formula for trapezoid, but I always find it easier to just break this up into a triangle and a rectangle. So what I do is I draw a horizontal line here, and I'm going to calculate the area of this triangle, and I'm going to calculate the area of this rectangle, and add them up. Okay, so let's start with this rectangle. That's the easy part. Its height is just v0, and its width is tf. So this is equal to v0 tf, okay, plus the area of this triangle. And a triangle, its area is 1/2 base times height. The base is again tf, and the height, right? Well, that's nothing but the change in velocity. That's just a tf. So this is 1/2 tf times atf. Or in other words, x of t equals minus x of 0 is v0 tf plus 1/2 a tf squared. And as before, I can call tf whatever, I can call it t, and so I can just erase this. I get x of t minus x of 0 is v0 t plus 1/2 at squared. And again, I like to give this guy a name and call this x0. Okay. And once again, this should feel familiar from calculus, because if I took the antiderivative of this expression, the antiderivative of constant is t, the antiderivative of t is t squared over 2, I would get exactly that equation. Okay, so enough with the algebra. What does this look like? It's going to generically look something like that. The slope right here, that is nothing but v0. So this is the picture, the case when v0 is greater than 0. If I instead had v0 less than 0, I would get something that would look like this. Okay, hope you found that as fun as I did. I think this is a really amazing thing, is that given this very simple modeling, simple way of thinking about some physical system, saying that, okay, let's imagine its acceleration is constant. We can predict what its velocity does as a function of time and what its acceleration does as a function of time. And we'll do lots of problems where we make use of these expressions. But I really find this modeling task to be extremely fun and enlightening.